then when they end up getting 0 because they have copied from another gentleman or lady who has also got a 0 because they have made a mistake, then it becomes embarrassing. So really that is the problem. All wrong answers, all copied from each other and non-attending classes, then really it's a very tricky situation. So I don't know what exactly you guys are interested in, but I really can't beyond a point because I can't see you. I can't. Oh, seems to be. Oh. Okay. Well, doesn't matter. What I was talking about was the method of King Altman, King and Altman actually, to be fair, and essentially. The idea is that essentially it is a graphical method, and the idea is that you have a reaction, as I said, E plus S, let us say ES, and then going to E plus P or whatever, and suppose you have inhibition E plus I, sorry, is EI or some such thing, whatever. Then you actually have, sorry, EI. Then you actually have three nodes, E. Yes, these are the three. Started trouble right away. Can you hear me? Can you hear me?
Yes. Yeah.
Yeah. So then you can draw your make your drawings, and you can say E and so what did how did I draw it? So E, there is this E to ES, which is of course both forward and backwards. Then there is ES to E. This is E, remember. So there is one like E here, and there is an ES to EI. So these are the three nodes, and this is the drawing. And so then you can of course determine what are the ways in which E is forming. And the forward reaction is the pseudo steady state kinetic given by ES. The back one is minus K minus 1. Sorry, the back one is K minus 1. What the hell? This is becoming very irritating. K minus 1. This is K2. Notice that it is just K2. And this is of course EI, forward is K1, K, let us call it 3 or whatever you want to call it, K3I, and the reverse is K minus 3. Okay, and then you can write the basic formation equations. So E will form by various mechanisms, right? How will it form? Can you tell me? What are the, so E has the following. This is forming it, this is forming it, and this is forming it. Okay. What about ES? This is this forming it, and that is it. Okay. And what about EI? This is forming it. I mean down actually. So there's this one. So you can see that you can write up the basic equations and actually determine this. So let us do the more harder one, which I was talking about, which is that we had this suppose you have E plus and you have a two reaction mechanism, E plus A going to EA. Do you remember this? And then EA plus B going to EAB. And notice that EAB has then isomerization reaction, so we are not really bothered about if the product is PQ or not. Somehow it has formed PQ. So notice that we did not bother about this because these are fast equilibrium kinetics, EAB. So we call this whole thing as EX, whether it is EAB or EX. And EX then sort of gives up on EX So Ex then gives up on EP plus Q, and then EP plus Q then goes to EP plus Q, and then this then EP will go to E plus P. Really, right? And so we wrote the E, the EA, the EAB or EAX, the EP, and the EP and E. Yeah, so 4 of them, right? So E, EA, EX, and EQ or EP, whichever is lost first, right? And what are the reactions? What is the forward reaction here? It is K1A. The reverse is, of course, K minus 1. This here is, what is the forward reaction? K2, let us say B. The reverse is, of course, K minus 2. Right? What is the forward reaction here? Some K3. But what is the reverse reaction? K minus 3 into Q, if Q is got rid of. Are you getting this point? And then what is the forward reaction here? It's some K4, doesn't really matter. But the reverse reaction here is K minus 4P. Got it? So you have to remember that depends really. Now, really, and then set up the balance equations, which is actually quite tedious. I mean, I hope, let us actually, you want me to do this? We can do this. Let us actually do this so that you get a feel of what is going on. So for E, the following, so obviously they are the following. I mean, this has got the following sections. You cannot close it. You have to keep all the loops open. So this one open, this one open, this one open, and the top one open. Notice E is sitting here. E is sitting here. So this one here is this, and this. So let us do this one. What is this? Can I hear you? Somebody? K3 into, so let us look at this one here. Let us do the first one here. What is this one? K3, right? Into K4. K3, K4, this one, into this one, forward one, this one, K minus 1. This is this one. Okay. What about this one here? The second one? This and this into this. So this and this into this. So what is E again? Plus, what is this one? K4. Right? And what about this and this? This is K minus 2, K minus 1. K minus 2, K minus 1. What about this one? This is this into this into this. So this is plus K minus 3Q. What about this one here? K minus 2. And what about this one? K minus 1. So it's actually a tedious procedure, but it is actually very mechanical. What about this one here? This into this into this. Right? So this plus this reaction here, K2B. Okay. Then K3. And then this reaction K4. So for this most complex case situation, we actually have all these 4 reactions happening here, and we have to sort of, we can then, and then of course similarly we find, so we found out E, and so E by E naught, which is the total E naught, or rather the E naught. This E naught is the sum of all these terms here. So I will sort of call them some D, the denominator, right? And this denominator is rather large. And so really what we are saying is that we have to find out E by E naught, EA by E naught, E by E naught, EA by E naught. Okay, and then EX, this X that I wrote as EX by E naught, and E naught is nothing but this plus this plus this plus, of course, EP. Can you hear me? EP by E naught. EP by E naught. And E naught is the sum of E plus EA plus EX plus EP. And once you have found that out, then of course, what is the velocity? Velocity is dP by dt, which is K3. I hope you realize this. What is the velocity? K3. This is the one which is giving up Q, right? K3 into EX. And of course, that depends on if you're looking at P, if you're looking at dP by dt, or Q, if you're looking at dQ by dt, and whether you're looking at dP by dt. These are all both important things. What is, they may or may not be equal, but they should be because they're stoichiometrically balanced in this case. But in general, they may or may not be equal. So minus K minus 3 into EP into Q. You get the point? So dQ by dt is equal to K3 EX, because this is the part which is generating Q. And so what happens is that when you write all these things, what it does is that it does become very tedious. But really the point that I'm trying to make here is that this is a very standard method of finding out the fractional saturation. A graphical method which is preferred by biochemists, and you should be aware of this. It is the attempt to find out the fractional saturation. It is a very tedious method, but finally many of these terms will tend to cancel out, and you really, what you are interested in is not some complicated procedure, but let me sort of wipe this out and say that really what you are interested in is the shape of the reaction. Because you do not know K1, you cannot find out these things, K3, K4, K4, K2, K3, K2. You're not interested. You are interested in these as lumped parameters. So what you are interested in is how does the reaction look like? I mean, when you do a velocity plot and your substrates A and B, how does it look like? Is it something like K1A minus plus K2B? Or is there a minus K3 P minus K4 Q? Or is it more complicated? It is K1 A plus K2 B plus K2 B plus K3 A into B, and there is a P into Q term. So what are the terms? After all, these parameters here, K1, K2, K3 can be determined experimentally. But if I don't know the shape of the function, what is this function as a function of A, B, C, and D? If I do not know the function, I cannot perform my experiments. I cannot determine parameters. Is it K1 A square plus K2 B square plus AB plus A plus B? And is there a denominator? Now, this methodology allows you to then create the structure of the function. This function, what is this function, is the most important thing. because then the parameters can be determined as lumped parameters. So it turns out, for example, that I will clear it actually, so this is much simpler. Actually, it turns out that velocity is something like some k1, k2, k3, k4, whatever, etc., etc. Some constant k, which is k1, k2, k3, k4, whatever, or and E naught, of course, some constant k, and of course E naught, which will bring about the B max business, okay, into A into B, minus some other constants. Wrong here today. Minus some other constant, some k prime, sorry, I'm doing the mistake here, minus some other k star, which would be possibly k minus 1, k minus 2, k minus 3, k minus 4, and so on and so forth, and into pq upon some determinant, or sorry, denominator. So we know the shape. So it is, so of course, again A, E naught. So we know that the velocity is k into E naught AB, k into k star into E naught PQ upon denominator. But what is the denominator also is very important. So these are the steady state equations. So we really are saying that therefore this sort of thing takes the form of some E naught here, which you know, and then some constant capital K. अरे क्या हो रहा है यार? Some constant capital 1, let us say, into A into B, minus some capital constant K double star P into Q. Okay, and then there is a denominator, and unfortunately this denominator is actually quite complex, because the denominator, unlike the numerator, which contains AB terms and PQ terms, AB terms and PQ terms only, the denominator contains everything. It contains a constant C plus C1A plus, you know, C2B plus C3P plus C4Q. I hope you understand that. And then, of course, the other combinations plus C5AB plus C6PQ, but not just C6PQ, but also, sorry, PQ I wrote like that, but that's all right, plus C7, the other combinations, AP plus C8, AQ plus C9, BP plus C10, BQ. BQ. You get the point? So all possible combinations are there. A, B, C, D are there. A, B to P and Q. That is to say, then AB is there. AB, AP, AQ is there, and then in all combinations, AB, PQ, AP, AQ, BP, BQ. So obviously, this is the form of your velocity equation. And so, in a complex situation, you will now need to determine all the values. This C, C2, C3, C4 are lumped parameters. You know, they would be K1, K2, K3, K4, the basic equation that I wrote. So it's the shape of the equation which is important. Without the shape, you cannot do any modeling. Anyway, you will not know the intrinsic K1, K2 parameters, so you will have to determine this experimentally. It is this point that I'm trying to make. Are you following this? As a matter of fact, let us think about it a bit more clearly. I mean, I have been writing all kinds of equations, and I think you people have not been. What about the equations that we wrote for, let us say, reversible Michelson-Menten kinetics, the simple reversible equations? Do you remember them? Can you tell me, any one of you? What was the reversible Michelson-Menten kinetics? You remember what was the equation? V is equal to एक second में something seriously idiotically wrong. What is V equal to? Hello? What was it? What was the reversible Michaelis-Menten? Vf 1 minus rho. Come on. S by Ks. If I remember it, then I'm sure you should be remembering it. 1 plus S by Ks, right? Plus P by Kp. Do all of you remember this expression? Hello?
Yes, sir.
Hello? Yes, sir. Yeah. So can you tell me now, what does this form take? What is this form? What is this form in terms of its simplest parameters? Remember, rho is equal to P by S upon P equilibrium or K equilibrium, which is P equilibrium by K equilibrium, S equilibrium. And also remember, P is equal to S naught minus S. Okay, let us do the simplest part of it. So, what is this term here? What is this term here? Into S by Ks, let us say. Forget the denominator for the time being. Let us do it one at a time. What is Vf? And of course upon Ks, let us say. But we can keep this as a constant, that's all right. That's not a problem. S into 1 minus rho. What is S into 1 minus rho? If I wait for you to reply, then I think the classes will go on for 5 hours. S into 1 minus rho. Where we know this. And so this is S into 1 minus rho is S naught minus S upon S divided by P equilibrium by, which is S naught minus S equilibrium upon S equilibrium. Can you simplify this term for me? And can you see now, which is much more important, can you sit down and simplify this? And can you see, or without even actually doing this algebra, can you see that this is some Vf star, where everything else is a constant in terms of S naught and S, that we have something like S minus S equilibrium. Because notice that this term goes to 0 as rho approaches 1, which means as S approaches S equilibrium. As S approaches S equilibrium, rho approaches 1, because P will also approach P equilibrium from the other side. As S approaches S equilibrium, P will approach P equilibrium because of this basic equation. And so therefore P equilibrium is equal to S naught minus S equilibrium. So as S approaches S equilibrium, P will approach P equilibrium and this reaction rate will go to 0. Because 1 minus rho will go to 0. So this is the form that we are essentially looking at. We have S minus S equilibrium, where this term, how far is it from equilibrium is how the reaction rate is determined. So I can think of this as some kind of S star. As S minus S equilibrium. And write this whole complex business here as some kind of an S by Ks, P by Kp. Again the same way. P is related to S in terms of this here is nothing but S naught minus S. And Ks and Kp are related by the Haldane equation of Vf and Vr. So as far as we are concerned, we can convert this equation, and I want you people to go back and try it. We can write this as V is equal to V max S, but we write S star Km star plus S star, where S star is this. Because remember, this reaction will go to 0 not when S goes to 0. Normally it goes to 0 when S goes to 0, but when S star, S approaches S equilibrium. That is all that is it to it. This whole expression has been derived to say that, hold on, normally reactions go to 0 when S goes to 0. But now, when S does not go to 0, but S approaches S equilibrium, this reaction has to go to 0 because the reverse reaction will become dominant. Okay, so this simple transformation of S to S star, and we can write this as the form of the equation here. So as far as we are concerned, we have to determine some Vm star and Km star with respect to S star, where S star is no longer S, but S minus S equilibrium. Because we also know from our basic algebra as well as our basic understanding of reversible reactions that V goes to 0 not when S goes to 0, but when S star goes to 0. S minus S equilibrium goes to 0 as S approaches S equilibrium. So you can see that this is the kind of kinetics that we develop. Do you follow what I'm trying to say? Without doing this algebra here. So we can write this whole thing as some S minus S equilibrium, and everything else will be in terms of S naught and so on, S equilibrium and so on and so forth. Can you do this for me? Or should we do it in class? Is this algebra obvious? From intuitively, is it obvious that as S approaches S equilibrium, we will go to 0, and therefore instead of S, we use an S star, and instead of Km, we use a Km star. Because this is what we need to then determine for reversible enzymes. As far as the practical, see, it is one thing is important to find out the mechanism, but even more equally important is to simplify this mechanism to find out parameters which can be experimentally determined. Same with remember external diffusion control. All these expressions, notice. Actually, not all, but most of these. For external diffusion, again, we wrote Vm S upon Km apparent star plus S, where Km star is really incorporates the fact of external diffusion. Similarly, we wrote for internal diffusion, where we wrote Vm x upon Km some double star, some K double star plus S, where this incorporates the fact of internal diffusion. So when we do actual experiments, we try to simplify the equation into the simplest version that we can get. If this is the simplest version, where these have changed, or S has become some S star, or Km has become some Km star, or Vm has become some Km star, incorporating a combination of features that impact on them, that is the job. Remember, internal for competitive inhibition also we had Km star, but that was a different Km star which was derived from Km into 1 plus I by Ki or some such thing. For internal diffusion and for external diffusion, the Km is a different thing. They're derived from different ways, but the impact is the same. So I want you to feel the point that I'm trying to make, that all these are reducible to the simplest versions, and that is what we are trying to do in our King-Altman. In King-Altman also, we are trying to get the form of the equation. The simplest form of the equation for internal diffusion velocity being measured against substrate concentration. This is the plot that we get. And from this plot, we can find out Km star. And from this Km star, then we can find out our internal and external diffusion or inhibitor concentration, etc. etc. So the shape of the equation is derived from fundamental principles that we are developing. But the parameters after the shape of the function has been, or the function has been determined, are determined by experiment. And then for determination of parameters, we can lump all the parameters which can be put together into one single block parameter. Am I making sense? Or is it too fast? Hello? Let us solve some problems. Hello, all of you are silent. Yeah, I mean, my problem is, as I said, my problem is that can you solve problems? Can you now, let's sort of rub this out. If it is clear, I mean, if I don't get a response, I assume that it is clear to all of you. So can you determine, for example, the form of equation when I have E. Can you understand when this would happen? Let me say that this is the equation, which is essentially saying E plus A goes to EA. A plus B is joined, and let me say it is one-way reaction. It is joined by a catalyst to make AB, or let me call it product X or X. See, there are many reactions which are conjugation reactions, right? A plus B is giving X. And I can ask you the reverse problem also. X gives P plus Q instead of A plus B. So can you see that this okay? E plus A is EA. EA plus B is equal to EAB. And then EAB goes E plus X. So is this all right? And I want you to find out the rate at which X forms. What is the form of the equation? Now I want you to prompt me. Let this be K. Let this be K1 A. This is K1 K minus 1. It really does not matter what terms you use. And then you write K2 K minus 2, and write this as K3. Okay, both the enzymes bind. So the enzyme is like something like this, and then A comes here, binds, and then B comes here, binds, and then they join together and they leave as some kind of product D, X. So it takes two molecules together, joins them together and sends them out. That is the mechanism. So we are saying that whether A binds first or B binds first, they bind sequentially. This is the kind of model we can develop. So E becomes EA, EA becomes EAB, and then EAB releases E plus X. Is this all right? So now this is K1A, this is minus K1, this is EAB. I hope you realize that this is E, this is 1, this is EA, and this is EAB. So this is EAB. So this is for, sorry, इसको A को backward करना पड़ेगा, है ना? So this is plus B. So this is EAB. So this is forward. The backward will be minus K2 or K minus 2. Sorry, but the forward will be K2B. And now this reaction I'm saying is non-reversible because of large delta G. So there is no K minus 3. There is only forward, and that is what? That is K3. Okay? There is no reversible reaction because delta G is large. Now can you tell me what is E? So what are the things that we will get? What are the three? This is the basic master diagram. Notice this reverse is missing. Okay, so we have this, but this, but only this. Okay, so tell me what is E, tell me what is EAB, and what is EA. And so what is the form of this equation? What kind of velocity velocity is a function of A and B and not of X? Notice that reversible reaction is not there. So what is the form of this equation? That is the question that I want to ask you. Please, can we go ahead and ask what is E? Can any of you sort of volunteer, or shall I have to do it myself? So notice that E is from here, this is E here, EA and EAB, or EAB on EAB becomes EX. You can write that, but that, as I told you, is an equilibrium reaction. So EAB we can write it as EX then E plus X, but that's really not important. EAB to E plus X. Because remember, as far as I am concerned, EAB and this is EX. These are, both of these are together. So it's E plus X. So this I have noticed, and notice I have just sort of conflated the two. Okay. So one is, so E will be, one will be this. Are you following and being quiet, or you are not following at all? Let us have this answer at least.
Sir, I am not following. I don't know about others.
So then you have kept quiet and you have thought that ये सब बेकार की बातें हैं. What is it that you don't follow? Did you attend last class of King Altman?
Sir, I am lagging, so I am not able to follow.
But did you attend the last class of King Altman method? No.
No, sir.
हाँ, तब तो फिर थोड़ा मुश्किल होगा ना. तो फिर आपको पूछना चाहिए कि सर आप 1 सेकंड में बता दीजिए किंग ऑल्टमैन क्या होता है. किंग ऑल्टमैन इज अ ग्राफिकल मेथड. अगर आप ये पूछेंगे नहीं तो फिर कैसे पता चलेगा, और आप शर्माएंगे कि हमने क्लास अटेंड किया. भाई साहब, आप चिंता क्यों कर रहे हैं? 90% people as a first approximation, nobody attends the class, isn't it? As a first approximation of class of 60, first approximation अगर आप engineering approximation करेंगे तो मैं कहूँगा कि सब लोग absent है ना. तो इसलिए अब I think no point being embarrassed about it. So the King-Altman method is essentially a graphical method to find out, and there are certain rules. First, you make the master structure, and then you have certain rules. What are the rules? So all the lines that lead up to A or EAB or EA, which are the nodes, and these are the nodes, and these are the you've heard of nodes and arrows and edges, nodes and edges. So this is the master structure. So the previous one was, this was the master structure. So first of all the lines that you will draw reaching to these nodes will consist only from the master plan. So ये आप उल्टा पुल्टा ड्राइंग नहीं बना सकते. जैसे कि अगर ये मास्टर प्लान है, if this is the master plan, then you cannot draw an arrow like this. ठीक है ना? तो and lines only from the master plan and these lines will either be normal K1, K2, K3 or pseudo first order reactions. For example, E से EA बनने के लिए K1 into A है ना, EA बनने के लिए reverse is K minus 1. So simply E to EA, the pseudo first order reaction is, it's actually K1 into E into A. But we can write it as a pseudo first order in terms of E alone, we have to write it. So if we want to write it in terms of E alone, then you write it as K1 A, which is the first order reaction constant, into E. The reverse reaction is K minus 1 into EA, so that's not a problem. So that's just K minus 2. So here notice I have written K1A, the forward reaction, K minus 1, because these are the nodes in K terms mein we have to write first order reactions. EA to EAB adds the B, so we have K to B forward, the reverse is K minus 2. And here this is K3, that is all. So now the first rule is that you write in all the lines, all these fluxes, all the edges in terms of first order reactions or pseudo first order reactions, and all the points making these edges will consist making these nodes from these edges will consist of lines only from the master plan. Only the edges that are there in the master plan will be used. Only these edges will be used. And you have to connect every pair of enzyme forms, all the pairs of enzyme forms The enzyme forms here are E, EA and EAB. All of them have to be connected, and there should be no closed loops. So closed loops you cannot use. तो closed loop तो फिर आप यहाँ से यहाँ जाएंगे, यहाँ से यहाँ जाएंगे, यहाँ से यहाँ जाएंगे और वापस चले आएंगे, तो ये तो गड़बड़ हो जाएगा ना. तो no closed loops. Okay, so the triangle, for example, in its general principle, ये क्या आ गया? Clear. नहीं भाई, sorry. Clear canvas. So the triangle, for example, consists of, what are the non-closed loops for a triangle? There are only three possibilities, right? What are the three possibilities? 1, 2, this one is off. 1, 2, this one is off. I hope you know the third one. 1, 2. These are the possible combinations. Now you want to reach E. How can you reach E? This. For this E, this and this. And how can you reach here? This and this. Okay. We'll come to that in a minute. What about EAB? EAB is here. No, ये तो EA है. Sorry. What about EA on this edge? This edge. This. And then this. These are all will reach this corner, EA. What about EAB? EAB is this edge, this corner here. So how will you reach this corner here? This. One way. Then what about this and this? And what about this and this? Is it becoming very obvious or is it becoming too childish? Let me stop here for a moment. Can you see?
No, sir. Yes, sir. This I can understand.
Now you can understand. So right, अब इनको terms में लिख दीजिए, equation के terms में. इनको equation के terms में लिखिए, क्या होगा? मैं इसको मिटाना नहीं चाहता हूँ. अभी कोई जगह नहीं है, बट ठीक है, कोशिश करते हैं. तो E का लिखते हैं. E का बताइए क्या होगा? चलिए आप लोग बताइए. E ये है, तो ये E ये यहाँ से ये क्या है? What is this one? K2B. E का मैं लिख रहा हूँ, है ना? E का है ये वाला K2B. K2B था ना? हाँ, K2B into K3. ये हो गया प्लस ये क्या है? K3 और ये वाला क्या है? K-1. ये हो गया, ये K-1 है, ये K3 है. फिर ये वाला, ये क्या है? K-2 into K1. Sorry, K-1. ठीक है ना? ओके, ये वाला हो गया. तो E का ये हो गया इक्वेशन. अब EA का बताइए. EA का है ये वाला. दिस इज K1A. ये वाला कर रहा हूं, K1A इंटू K-2. ये हो गया. फिर ये वाला नहीं, हाँ ये राइट. सो K3 प्लस K3 है ना?
K-2 नहीं, K2 है सिर्फ.
हाँ,
K-2 नहीं, EA में सिर्फ.
EA में K1A और ये
K2
K-2 होगा ना?
K2 है सिर्फ.
Yes, sir. K-2.
ये तो K2 ऊपर वाला लिखा था, ये तो K2B इधर है. ये की बात कर रहा है. कैसे? ये तो K2B है इधर. ये वाला फॉरवर्ड वाला K2B है, रिवर्स वाला K-2 है.
सर वो जो ऊपर क्वेश्चन लिखा है E से EA प्लस B से EAB, उसमें K2 है वो.
इसको मैंने K2 लिखा था,
Yes,
ये तो
sir.
रिवर्स रिएक्शन है, तो K-2 लिखना चाहिए था ना, क्योंकि फॉरवर्ड रिएक्शन EAB ये K2B होगा,
Okay, sir. Okay, sir.
राइट? तो so this is it. So EA का हुआ K1A into K2, ये वाला करेक्ट हो गया, फिर ये वाला हुआ K3 और ये वाला क्या है K3 और ये है K1A, है ना, K3 K1A, और तीसरा क्या है ये नहीं, हाँ यही तो है ना, ये अब ये देखिए, ये इंटरेस्टिंग है, ये इंपॉर्टेंट है. नाउ नोटिस दैट दिस इज 0 बिकॉज ये एग्जिस्ट नहीं करता है, दिस डज नॉट एग्जिस्ट ना, दिस रिएक्शन डज नॉट एग्जिस्ट, दिस इज 0, सो ये पूरा 0 हो गया. आप मेरी बात समझ रहे हैं? अगर ये रिवर्सिबल नहीं है, ये वाला रिएक्शन नहीं है, दिस इज द पॉइंट दैट आई वांटेड टू एम्फसाइज. ये वाला तो है ही नहीं ना, ये एग्जिस्ट नहीं करता है, ये वाला, दिस वन, तो ये 0 हो गया, तो ये 0 हो गया और कुछ नहीं है, देयर इज नो अदर टर्म बिकॉज दिस इज गॉन. सिमिलरली EAB में देखिए ये एग्जिस्ट करेगा, सॉरी ये एग्जिस्ट करेगा बिकॉज ये ठीक है, विच विल बी दिस प्लस दिस, ये वाला एग्जिस्ट नहीं करेगा क्योंकि इसमें ये डायरेक्शन है एंड दिस रिएक्शन डज नॉट एग्जिस्ट, सो दिस विल नॉट एग्जिस्ट. आर यू गेटिंग द आर्गुमेंट? बिकॉज ये नहीं है,
Yes.
एंड दिस वन विल आल्सो नॉट एग्जिस्ट बिकॉज ये नहीं है.
Yes, sir.
ये E to EAB तो है ही नहीं ना, तो ये पॉसिबिलिटीज ये सब गायब है, तो EAB का सिर्फ ये वाला टर्म होगा, दिस एंड दिस, which is equal to just this and this. Notice that all other methods are gone because one of the steps does not exist in the triangle. You getting my argument? So EAB
Yes, sir.
will be only this and this, only the first, that is K minus 1, sorry, EAB, ये वाला, sorry, K1A, K2B. So K1A, K2B, that is it, nothing else. You get the argument?
Yes, sir.
So notice E had 3 terms because all 3 existed. EA had 2 terms and EAB had 1 term. Because this triangle was not, as was the earlier case, this triangle here, earlier जो भी हम बना रहे थे उसमें सब में forward backward reactions थे, ये अगर सारे होते तब ठीक था, लेकिन now notice that this fellow disappeared, so only one forward, so कई सारे possibilities यहाँ से rule out हो गए. Okay, and then we can simply find out the rate of reaction. Okay, let us stop here and you solve this out. And so really, as I was telling you, the form of reaction is what is important. Thank you. Let us stop. So it's a rather simple method once you learn it and practice it. So King and Altman, ये सारे simple biochemists जिनको maths नहीं आता उनके लिए है ये. आप लोगों के लिए तो बहुत आसान है, आप मैट्रिक्स करके कर लीजिए, लीनियर अलजेब्रा लगा लीजिए, फ्रैक्शनल सैचुरेशन के इक्वेशंस लिख लीजिए, you will come to the same. This is the algebraic method, a geometric method which actually biochemists prefer because they find it very difficult to handle algebra. So I will not go about this anymore. I think I will stop here. So once you understand the technique, it seems obviously any new technique takes a bit of time, but if you understand, if you have attended the last class and heard the last class and this class, it is so very simple and obvious. So it actually is more of an empowering tool for biologists rather than engineers to tell them that, you know, even complex reaction mechanisms can be modeled into a kinetic equation by this method. So really for you people, it is essentially redundant, but I thought I should expose you to this technique because why not use an easy technique if it is available? So it's actually to make things easier, not make them more complicated. So once you get the feel of it, you understand what the hell is going on. And it's very mechanical, though it's slightly tedious if the number of steps are larger. So is this clear now? Shall we stop here? Thank you.
Yes, sir. Thank you, sir.
Thanks. Thank you.
Thank you, sir.
Thank you.